The next step, we want to include a so-called pooling layer. And before I'm going to do that, I want to go back to our code because in the last section, we were testing our convolution layer and got a few nice plots. Just quickly want to show this again. So we sim show, and then we passed our images through different convolution layers. And they generated an output matrix. And let's take a look at one of those images again. Brackets, of course. And then we have these images here. And the idea also was that we, during the training process, we load so-called mini batches of those images because there are too many images, 25,000, and would be too much to run them through the network at once. So that's the reason why we load so-called mini batches, and we set up this function here. And the class that reads the mini batches randomly from the larger set of data. And we tested this this class, but since we wanna run this many times through the training process, so that ideally with many calls of the mini batches, we eventually will cover the entire data set. It makes more sense to restructure the code a bit. And that's what I did. So I added to the read and scale part an init part. And in this init part, we now give the mini batch size and the A and N size because these two parameters do not change during the training process. We want to save those quantities. Then we search for our location, or we point to the location of our data set. As discussed earlier, we create lists of the data sets, so of the images in this case, and also of the classes. And we also want to store this so that we run read and scale during the training process. We don't call these quantities and variables anymore because we need to do this only once. So that's the reason why I added this init. I want to show this init again. Did you see how I changed the code? And again, if that's somehow too fast or so, you will see I will put everything on the GitHub repository, and then you can just copy and paste it. And the actual read and scale part, so the header of this part looks like this. So we have the A and N size, the mini batch size, and then we pick the mini batch randomly, and that's what we do many times throughout the training process. So we will call read and scale many times throughout the reading process. So that's one thing we should do first. So for testing, of course, we had a different structure, but now for using it in our A and N, we should have such a kind of structure in our read and scale class. Okay, and we can test and run it now. So now we give the mini batch size and the A and N size while we are initializing our class, and the mini batch matches are extracted when we just call read and scale. And really just run this more than once so that you also see that the images which are extracted are also randomly extracted, and you always have different images. So I test run it again. And here we have our image. Apparently it's a cat. And now it's come to the actual pooling layer. So let me just move to the slides again. So the pooling layer. So what is a pooling layer? And it's often it follows often after a convolution layer. So there are two main ideas actually. So the first idea is to reduce the variance in the image and also the complexity for computation, because probably we don't need all the information, or there's some or there's a way how to extract more important information. And there are different ways how to do that. One way is the so-called average pool. So you, like in the convolution part, you have different kernels that go, or you have a kernel that moves over the image, but then you do not calculate the convolution. No, you just extract or calculate the average within this particular kernel, within this particular region of the image. And this is the new data point, or that's the pixel value for the new image. And then you move on step by step. Again, here you can have a different stride. And every time you calculate the average, and this value is the pixel value for the new image. What it actually does, if you think about it, since it's calculating the average, it's blurring the image, which is helpful for reducing edges. So we, in some cases, we might want to do that, but it's not in our case. Then there is the so-called max pool layer. And instead of calculating the average, it takes the maximum of those windows in the kernel for the image. So it has a certain kernel size, let's say 3 times 3, and then we just keep the maximum, and the maximum value in this region is the pixel value for the new image. The advantage is that usually objects in the background have small or lower pixel values, whereas objects in the foreground have larger pixel values. And therefore, since you only store the maximum values, it enhances objects in the foreground and reduces background. And that's probably what we want to need here in our case. However, then take into account, it just does quite the opposite. If for some reason the pixel in the background have higher values than those in the foreground. For example, our cat or dog has dark fur, but is sitting in front of a white wall. But still, you can distinguish between background and foreground. And there's the opposite. Mini pool does the opposite of the max pool, if you want. So again, what is the idea? So we have a certain region in our image, and we just take the maximum or the average or the minimum, and that's the pixel value for the new image. Then we just move on with a certain sprite and do exact same thing. So it's technically almost the same process as convolution. And that's the reason why we can set up a new class, the pooling layer, by mainly copying, pasting much of the code that we have already in our convolution layer. So we set up the class maxpool, and again, I want to just go to the code first and on the slides, and then we want to program the code or write the code together in our user interface. So what is the structure of maxpool? So we want to have a forward part, and later also we want to have a backward part. The input, of course, is our image M. We need a stride and also the shape of the kernel. What doesn't make sense is padding, because we want to have the maximum of this particular patch. And if we add padding, then we will add 0. So that doesn't make sense. And also here, we need to have the shape of the image. So X and Y coordinates, the number of channels, and the number of images. Since we pass the information from a convolution layer to a maxpool layer, so the maxpool layer will come after convolution layer. Number of channels refers now to the number of kernel that have been used in the previous convolution layer. And for the purpose of backpropagation, we also want to save the inputs. And we also want to save the inputs just for checking whether the maxpool layer does the right thing. So that's the first part. And Then there's the part where we essentially just copy and paste what we have in the convolution layer already. So in the convolution layer, we have 2 lines where we calculate the size of the expected output matrix. And the same equation applies. The only difference is that we know the padding is 0, so we can remove this part. And we also don't need this part because we also don't need to provide a padded image. So we can remove this part. So still, we want to actually call this image then image padded, even though it's not a padded image, but we can use this variable then throughout the code, and we don't have to change all the other things. So it's just our image M, which has padding 0, if you like. And based on the calculations for X and Y output, and we know the number of channels and the number of images, we can now reallocate our output matrix with NP zeros. And then there's one thing we need to do. We need to copy our padded image because we're going to need this for the backpropagation. When we come back to the backpropagation, we will see that we have to store the location of the maximum. So where the maximum in the original image came from. And that's what we want to do in this matrix or array that we call image padded copy. And I want to show you how to create this mask. So this mask contains the information of the location of the maximum. And then later in backpropagation, you will see why we need that. Now, you in principle can think about it. It has to do with the derivatives, of course. Okay, so we just go to our convolution layer or convolution class, copy and paste what we need. And in this case, of course, we need these nested loops. And we also need to calculate the start and the end point in our batch. There's one thing we could actually do. We can save it in another variable named sx and sy with the command slice. So in Python, it's a Python command. It immediately understands that this is a slice, and it slices the data accordingly. So we can now use these coordinates in extracting the current slice from the current channel. And instead of multiplying then the image with a filter, we just take the maximum. So then we have our max pool. Right? That's it. And the maximum of this value is the pixel value from the new image from the output image. So we can directly just store it in the output image. So the main difference is here that we do not perform the calculation NP multiply and then sum. The only difference is that we now just take the maximum. And here's the point that we want to store the location of the maximum. So there are probably many different ways how to do that. So one idea is to say, to use this function NP equal. What does it do? So it compares the entries in a matrix to a value. In our case, our matrix is this sliced part here. And the value is our maximum, of course. And it returns a matrix with ones where this statement is true and zeros where the statement is false. So that's actually pretty useful. But the problem is if you move with your window step by step, so for example, only if you have stride 1, then you might cover a region where you have a different maximum than you had before. And if you just use NP equal, it will forget the maximum because now we have a different maximum, might be larger than the previous one. So it's overriding the previous maximum because as it says, it returns only zeros and ones where the statement is true once, where the statement is false, not once. So in order to avoid this, we just do not say equal, we just add. So it always adds up. So you thereby actually count how often a pixel contributed to the maximum. So how often was a pixel a maximum? If that's still not clear to you, I will show this later once we have our code and we can test the code, and I will show you what I mean. But the point is, again, I have to remember where this maximum was. And an easy way is to look where the statement is true, but then we just add up and count how often one pixel contributed to the maximum. Because later we can just, when we have our mask, we can normalize our mask. So therefore we have our mask. So every time a pixel contributed to the maximum, it says 0, it says 1. If that's not the case, it says 0. And then of course we want to save all the information like the kernel shape, the output of course. We need a stride later for the backpropagation part. And we also want to save the mask because we really want to make sure that everything works. And that's the idea. So, and after that, we want to test the layer. So let me just therefore go back to our other screen. So here we are. And let's go back to our code here. And one more thing we actually also should do is to set up a new folder as usual, for the same reason as usual, so that we can keep everything in order. So we just go to convolution and then just add a new folder. Let's call it max pool or pooling. Okay. So we just move to this folder and navigate to the folder. Save it here. And save it here. Okay, so now let's set up our pooling layer. So I want to add the 2 lines here again, because you can see already we add more and more functions to the code, so it's getting longer and longer, and we even don't have the backpropagation for most of the part. So we just set up our class, maxPool. In principle, you could be even more flexible and just set up a class we just call pool, and then we can pick whether we want to have a max pool, an average pool, or a min pool, because it's at the end just one line that's different. So that's something you in principle could do as a homework if you like. So we have the forward part, where as an input we need, of course, the matrix, then stride. Let's say we set it to 1 as a default, and the kernel shape. And let's say 2, that's a typical value. And then, of course, we determine the shape of the image. And then we have our variables again. So in principle, we could actually go to the convolution layer here and just copy and paste everything that we need. So we can, for example, just copy and paste this part here. So we just copy and paste this part. Then we have all the information we need from the image. And also we want to save the inputs for backpropagation and also for checking. Then we also have X and Y from the current shape. So we just copy and paste this part. Here in this case, of course, you get it directly from the input. and it is usually a quadratic kernel. Okay, so now we know the stride and the kernel shape, so we can prepare the output matrix. So we just go to output. And actually do another thing, we can just split everything now. And then we can directly compare the current layer with the convolution layer. So we just go to the part where we determine the size of the output matrix. We don't need a padding, of course. So that simplifies the equation here. So we don't need a padding. And therefore we just say image padded equals m, that we can just use the variable name. And we don't have to change all the other things. Okay, so we have our X and Y output coordinates, so we can just copy and paste the part where we pre-allocate space for the output. So NK, number of kernels, that's the number of channels here, which is now the same thing, right? Because we do not perform convolution, so we don't change the number of channels. So that's equivalent in this case. So then we want to add this image padded copy. And multiply this with 0, because that's what we're gonna need for our mask then. All right, so what would be the next step then? So the next step would be this here. So we just have our nested loops. And then we just add the nested loops. And of course, we want to see whether it makes sense. So we probably have to change a few parts. So what do we need to change? So we don't have to go over the number of channels and over the number of the number of channels and number of kernels separately, because we do not add. Sorry, that's a typo here. So we do not add different channels like in the convolution part. We just calculate the average, and that's the reason why we can save one of those loops here. So we can take this part and shift it further to the left. So the image padded also is still our image m. Yeah, that's the reason why is that, well, we can just rename this variable, so we can just reuse this part here. So since we don't have an extra dimension for the kernel, we can also just remove one. The only thing that we have to take care of is being in a so having so keeping track of the indices. Okay, so then we can just do this one thing with the slices that I also showed. So we can now say Sx equals slice x start and y start. Sorry, x start and x end. So that's something you don't have to do, but I also want to show you that there's the slice function you in principle can use. and then we calculate the current slice. So that's what we did here as well. We just say current slice. And instead of slicing it like this, so like the typical slicing in Python, we can just say image pad and then apply those slices as X, as Y, and for the particular channel C, of course. So X, Y, C, and then we do this for every image. So that's the current slice of the current padded image. Again, we have our image, or all images. Then we have a copy, we create a copy for later. Then we select the current image. And then we calculate the slice of a particular channel of the current image. So now we want to determine the maximum. And that's what we can do with current slice max. And we just want to make sure that's a float. Because then later we want to normalize, and of course we normalize integer numbers, but still we want to make sure that this operation always works. Yeah, and then we can store the result in our output matrix. So it's X and Y. It's for particular color channel C. We don't have an extra kernel dimension. And we have our image I, and that's just the slice max. So in these, this line here, 181, that's the only difference, or it's the only line that differs if you have an average pool or if you have a minimum pool. So now we want to keep track of the maximum. We should probably write a comment like this, keeping track of those pixels which contribute to the max. And we can write for backpropagation. So that's not really clear for now, but we can keep it in mind. So therefore, we just take image padded copy because we want to know where the maximum came from in the original image, of course. And in the particular slice, channel and image, of course. And then we just use this NP equal. So maybe I need to shift this a bit. So NP equal and I want to have a line break here. So NP equal, and then we just go to the current image padded. Take a look at the slice. And take a look at the maximum. So let me just shift it further to the left, that you see the entire code. Also here, it turned out that make sure that's a float. And then we have our operations here. Okay, so we have our image padded. get the slice according to our step size we have here from the stride. Then we determine the maximum of the image in the slice. We save it because it's the pixel value for the output image. And then we just count how often a pixel contributed to the maximum. And then we just normalize our mask. We just say mask equals image. Edit copy. And then we can also normalize the mask. So we just divide the mask by itself. And of course, then we divide by lots of zeros, and we will get an error message or NNN warning. So we just add an arbitrarily small value. So if the value in the mask is 0, then you divide it by a small value, so it's still 0. If the value in the mask is not 0, if it's 1 or 5, then you divide it by the actual value plus a small other value. So it's still the number of pixel or the number of times a pixel contributed to the maximum. So you will still divide essentially 5 by 5, for example, or 2 by 2, so will be 1. Not exactly though, and that's why we add rounding here. So that might be not the most optimal way how to do that, but it's one way how you can do that. And that's it. So now we just have to save all those values we need. So let me just close this window that we can expand a bit. So we have to get out of the loop here. And now we have to save all those objects we need. So for example, we want to save the kern shape x equals xk. So that's always useful. Also, if you want to just check why the code doesn't work, why the error messages, why dimensions don't make sense. Then of course we want to save the output. The mask. And the stride. And we want to need this for backpropagation then as well. All right, so then let me just compile the code. Also want to show you that our module has some functions already. So we have the part with the reading the images, extracting a mini batch randomly, convolution layer, max pool, dense layer, then the activation for ReLU. We will add another activation function soon, softmax, all those classes we need for calculating the loss function and the cross entropy, and also the optimizer. So we have quite some code already. And that's why we should test it again. And when I do that, I would still run all those previous functions and classes as well, even though we haven't changed them. But I still want to see how it runs in combination with what we have added already. And That's the reason, and always might be something in between that we have forgotten and that we have missed, and that's the reason why I always want to run it all together. So we import our module, of course, and then we just read the images. And what we also have to do now is that we set up the first max pool layer. So let's call it MP1 for max pool number 1. And it should be now visible here as max pool. And let's stick to the default values first of all. So we have a size current shape 2 and stride 1. Okay, and we want to do this with different values as well. So let's stick to the default values first. And then of course it doesn't make sense to run everything in the second, so after the second convolution layer, because they're they have the same structure, so we can run the max pool layer, of course, already after the first convolution layer in order to test it. So we just say, let me just first of all initialize the max pool layer, and then we just call this max pool layer MP1 forward. Then the output would be, or the input would be the output from the convolution layer. Yeah, that's it. So we have our forward part. As I said, let's stick to the default settings, and that actually should work already. So let's see what we get. So I wanna just run. We ran this, but I just wanna run this part again, so we don't need this part here. And then I wanna run this part again. And let's see what we get. All right, so the code is done, and it produced the outputs from the max pool layer, and so it takes a while actually to run through all those images. So therefore, if you don't want to, so if it takes too long at your computer to run all those images, like in my case, it was 50 images here and 10 filters here. If it takes too long, of course, you don't have to do that with the same amount of same number of images. You can actually, of course, do this with fewer images. So for example, if you do this with 5 images and 5 filters, you still, of course, will have an result where you can really check whether the code does the right thing or not. So I ran it for those 50 images. So checked everything, and also this for 5 images again. And I want to show you the results. So we call the max pool layer. Then we read 5 images, pass them through the first convolution layer, and then the max pool layer. So what we should do now is we first of all want to take a look at those images. So I also explored a few images already, but I want to show you 1 or 2 particular images. So we want to take a look at the input, the output, and the mask. So remember, the input is just the convolved image after the first convolution layer. Then the output is the image after it passed the max pool layer. And then we have the mask, which stores the location of those pixels which have contributed to the maximum. So let me just take a look at those images, and then we also, of course, want to interpret those images. So first of all, that's our original image. So original from the from the convolution layer. So we can, for example, first of all, take a look at the shape of the output, which is the input of the max pool layer, so which is our image A1. And of course, we want to take a look at the shape, 98 times 98. So if we have stride 1 and padding 0, of course, and the kernel size is 2. So we should have 97 times 97 if you look it up in the equation. And our mask should, of course, have the same shape as our input image. It was too fast. 98 times 98. And that's the input image. That's the max pool image. And that's the mask. And kind of, if you just look at the values, you can kind of see the structure of this cat, right, based on the maximum. So it also helps to get some idea of the structure of these images. And also we want to see whether the code really does the exact thing that we wanted to do. For example, if you look at the initial image, there are lots of pixel values which are really 0. And there are other pixel values here, but we just want to have an image where we have lots of mixed pixel values because we really want to see whether it found the correct maximum, stored it correctly in the output image, and also store the information in the mask. So maybe we should do this with another image where we can really see that. For example, let's do that with image number 4. And let's take a look at those images. So, well, let's take a look at those images first. So that's another cat. And here we have the mask already. And let's take a look at those images. So the max pool was called with the default values, where the size of the kernel is 2 and the stride is 1. So the first batch in the image where you extract the maximum is this here. So the maximum is this value, 18,322.4. So if we go to our output image, that should be the first entry here. And in fact, it is the first entry. So that makes sense. Then the stride was 1. So we just move on to this particular square here. And the maximum is 19,000 and so on. And we see 19,000. And then moved on to the next step, and we have 19,500, 19,500. So apparently it works. And also if you just go on here, the maximum is 18,500 roughly. So that's the pixel value here. So it extracted the correct value and saved it correctly in the output image. But now let's also check whether we get the mask in the correct way. It looks a bit weird, but let's take a look at the values. So the first value, so the first maximum was here. So this pixel should be highlighted, and in fact it is highlighted. Then it moves on, and the maximum is here, so it should highlight this pixel. And it moves on, and the maximum is here, so it again should highlight this pixel, and so on. So it seems to work for one particular configuration, but we can also, for example, have another stride and another kernel shape. So for example, let's now run the same images, but now with the stride of 3, and let's say we have a kernel shape of 3. So we just run the max pool again with the same image. So the code is done, and let's take a look at the images again first. So it's the same image, so we can delete this part, and this part, and we want to leave those images as a comparison to the current one. So we want to display the input image, the output image, and the mask again. And that's the input image, that's the output image. Now it's a bit more blurred because the size of the kernel is larger, and also the stride is larger. So if we just now look at the shape of image number 2, the output image, it's 32 times 32. And we can also check whether the math makes sense. So the input image had the shape 98 minus kernel size 3, then divided by stride, and then plus 1. So stride was 3, plus 1 is 32, so it makes sense. Then the mask, however, looks completely different if you compare it to this, because the size of the filter is larger and the stride is larger as well. So both values are larger, but still, let's check whether it makes sense. So we have our input image again, so that's the same image. There's nothing new, but now the size of the kernel is 3 times 3, and then we look at the image, which is the output image. So the largest value in the box here is 19,200. So that should be the first value, and that's what we have here. Then the stride is 3. So the next box where we extract the value is the one I highlighted here. And the maximum is 20,300 and so on. And that's the next input. And let's do the same thing for the next line. And then we know it must be correct because it's just it's a repetitive process. So it's the maximum is 19,800. So if I go to the place, I have 19,800. So extracting the maximum works again, but now still we want to see whether the mask, which has the same size as the image, gives us the correct result. So the maximum came from this part. That's correct. Then we perform one more step. Oops, that was too fast. So we are here. And the maximum came from this pixel. And again, it's correct, and so on. So that makes sense. And it seems as if our max pool layer works. And I also want to go back to the PowerPoint to show you a few more results. So we have the original image, we have the max pool image, and then we have a mask. And then also when you run your code, please play it with different settings of the filter size and the stride length, and really make sure that the max pool layer does the correct thing. So when it extracts the maximum value, that it remembers it's from the correct place. And of course, it stores the correct value. All right, so that's our max pool layer. And we learned about different activation functions already in the last chapter where we created the core. And now I want to talk with you about other activation functions, for example, sigmoid and also the tangents hyperbolicus, which will play a role for this kind of problem.